Okay, this video we are going to look at a couple of things. We are going to look at two more types of calorimeters, and then we are going to start to look at Hess's law, and we're going to talk about additivity method. So last video we talked about a simple calorimeter. We saw that we had a styrofoam cup, we filled it up with water, and then we put our reactants inside of it. So simple calorimeters are great for most reactions, but where they're really not great is when we actually want to do a combustion reaction. And that's because we encounter two issues. One, you can't do combustion inside of water. And two, styrofoam is going to melt from the heat of the flame. So we definitely can't use a styrofoam calorimeter when we are dealing with burning something. So this is where we use what's called a flame calorimeter. So it's still going to operate off a lot of the same principles. We're still going to use water. The difference though is now the water is going to go inside of a metal can. And that's because we can heat the metal can. We can't do that with styrofoam, right? If we take a styrofoam cup filled with water and we hold that over a flame, it's going to burn a hole in the bottom, the water is going to go everywhere, and we're going to have a ginormous mess. So for the most part, this is kind of what your flame calorimeter is going to look like. You have whatever sample it is you're burning. So in this particular picture, the sample that's being burned is a candle, but you'll often see like a little alcohol burner, or like if you've ever seen those like old school lanterns where it's like glass and there's like a big wick that goes in and then you light that. Sometimes you'll see one of those under there. And then you have your calorimeter here. So this metal can, often aluminum, sometimes copper, gets hung above the flame. So the idea is the heat released by the flame as we burn our sample is going to heat the water, but it's also going to heat the metal cup. Okay, so that's where you're going to find one of the big difference with our calculations is we have to account for the calorimeter. With the styrofoam cup, we were kind of like, yeah, we're just going to pretend it's not there. But you've all heated water in a pot on the stove. You know that pot gets burning hot as well, right? So same deal here. This metal container is going to get really hot. So we have to account for how much energy it's going to absorb. So that means it's going to change the equation that we use. Okay, the other things you're going to notice before we start talking about the equation is you'll notice we kind of have this enclosing shield happening here. Okay, we have this to try to minimize how much heat we are losing. Right, remember at the start of the unit we talked about an open system, a closed, and an isolated. Okay, a flame calorimeter is totally an open system. We are going to lose heat, absolutely, but we're going to do our best to try to minimize how much heat we lose. And we do that by using what we call a chimney. Okay, and basically it's this enclosing shield that we put around it, and it's going to trap that heat. So as the heat from whatever sample we're burning comes out, right, normally it would kind of radiate all around. That metal can is going to trap it and force it to go up. Obviously, like I mentioned before, you're going to have huge sources of error because that metal can that you're using as a chimney to funnel the heat is also going to get warm as well. It's going to absorb some energy, and we are not accounting for that in our calculation at all, okay? And then obviously the air around it is sometimes going to get warm too. You'll find if we were actually at school, we would be using little alcohol burners and we would be burning alcohol samples to heat the water. And especially by the time we get to the propanol, you wind up with like flames shooting out the side here and flames shooting out the side there, at which point the heat from those flames is definitely not heating your calorimeter in your water, okay? So before we talk about bomb calorimeter, I don't really have anything in my notes about the equation, and that's because normally we would go do our lab. So what you're going to find for your equation is it's going to change a little bit, okay? And the reason it's going to change is we have more things absorbing energy. So we're going to call this delta CH, and we're going to call it a delta CH because this is a combustion reaction, right? Remember when we did the simple calorimeter, we said it was the negative MC delta T of the water? Well, it's still going to be negative, but now it's going to be the MC delta T of the water plus the MC delta T of our aluminum calorimeter or copper calorimeter, whatever it is. Okay, and that's because they are both going to absorb energy. They're both going to get hot, so we have to account for both of them. So that's kind of your biggest difference between a simple calorimeter and a flame calorimeter. Is it a simple calorimeter? I only need the MC delta T of water, but in this one, I also need to account for this one. So we're going to add them together, making sure that the negative applies to the sum of it. And some of you like to do that in a separate step, calculate what that is, and then put that number in. You definitely can do that. And then your last step would just be to get it per mole, right? So we would have to times by 1 over a mole, or potentially do like a mass and a molar mass kind of thing to be able to get it per mole. Okay, so some pieces are similar, some pieces are going to look a little bit different. Biggest thing, you need to read the question. Generally, if you see that the question is talking about a metal calorimeter, it's usually going to give you the mass of that calorimeter as well. And the reason you need the mass is you need to be able to do the MC delta T. Okay, so it's going to give you the mass. Usually the C is coming out of your data booklet because it's usually going to be like aluminum or copper, which are both in your data booklet. And the delta T of your calorimeter is going to be the same as the delta T of the water because they were in contact with each other. So whatever final temperature the water reaches, we're going to assume that the metal can reaches the same final temperature. We're also going to assume they both start at the same initial. So really, to be able to account for the metal part of the calorimeter, I really just need the mass because I'll already know what the delta T is, okay? All right, so other type of calorimeter is a bomb calorimeter. So we also use bomb calorimeters to determine molar enthalpy of combustion. Okay, so flame and bomb are for combustion, and the simple calorimeter tends to kind of be for everything else that isn't a combustion reaction. So bomb calorimeter is going to work on the same general principle as a simple calorimeter in that it's going to be that isolated system. Okay, the main difference is what it looks like. So skip a couple of slides. Here's more or less what your bomb calorimeter looks like. Okay, it's called a bomb calorimeter because it contains this little steel chamber, which we call the bomb. Okay, what we do is we put our sample that we want to burn inside of the steel chamber. We then attach, I don't want to say a vacuum because you guys get a picture like a vacuum you have at your house, but we basically suck all the air out of it and we put in pure oxygen because we want to ensure that the oxygen is going to be present in excess and it's not going to be the limiting reagent. Okay, so pure oxygen. Then we seal it all up and it goes inside this big calorimeter, which is filled with water. You then like screw the lid on. There's kind of that thermometer and that stir. I guess the closest thing to compare this to would be like if you have a pressure cooker or an Instant Pot, right? You're going to seal it all up because what's going to happen is as this reaction occurs, the pressure is going to increase significantly, okay? And obviously it's called bomb calorimeter because it does have the potential to explode like a bomb if you are not careful with it. So you're going to have little ignition terminals, and that's because your sample is inside of the steel chamber, inside of the water, inside of the sealed container. So you can't just like light it with a lighter. That's not going to work. So there's a little flick, you'll flick the switch, and then you just kind of stand back and watch. It sounds a lot more exciting than it is, but really you just stand next to it and you watch the thermometer rise. Everything is built into it. There's a stirrer inside, so you don't have to stir. You literally just wait. We obviously do not have any of these at the school. They're super expensive. I remember when I was in university, I think they were like 11 or 15,000. So I don't know how much they are now, but probably significantly more. But obviously the bigger hazard with these is just that safety piece, right? You have to really know what you're doing. It has to be maintained really well. There is obviously the potential that it does explode, right? Especially if you open it too early and the pressure hasn't released itself yet. So yeah, there are some hazards associated with it. So big difference between a bomb calorimeter and a flame calorimeter is the type of system, right? This is an isolated system. That flame calorimeter is an open system. So remember back when we talked about combustion, we said that the state of water would be different. So let's say I combusted, I don't know, methanol in a bomb calorimeter and a flame calorimeter. I would get completely different delta H's, okay? Part of why I would get different delta H's is one has more sources of air than the other, and I'm going to lose more heat in that open flame calorimeter. But the other reason I'm going to get some different numbers is the water is going to be in a different state. Okay, in the flame calorimeter, the water that I produce is going to be a gas. But in the bomb calorimeter, the water that I produce is going to be a liquid because of that high pressure. So automatically, because that water is a different state, the delta CH for my reaction is going to be different. Okay, the other big difference you are going to find, and not all questions will do this, but the biggest difference is you're generally going to find that the specific heat capacity of a bomb calorimeter is specific to that calorimeter. And that's part of why they're so expensive. They basically take into account how much water it's going to hold, how much all the metals weigh, and how much of each metal is inside of it. And so generally when you get your bomb calorimeter, it's going to come with a specific heat capacity included. Right? And that specific heat capacity is to be some number, where different ones are going to have different numbers, but the unit is going to be different. It's generally going to be a joule per degree C, or potentially a kilojoule per degree C. But you'll notice there's no gram inside of here. And that's because they've already accounted for the mass of all the different components in it. So really what that means is for me to be able to get joules or kilojoules, I literally only need to know what was the temperature change for this, okay? So this is where we're not necessarily using MC delta T anymore. We're potentially using just C and delta T, but it really depends on what units we had within that specific heat capacity. You'll find if you look at some old diplomas, sometimes they do that, sometimes they don't. Sometimes they'll be like, oh, it's a bomb calorimeter, but they'll just be like, this is the mass of water and this is the temperature change. At which point you don't really have a choice and you're going to do that negative MC delta T and then whatever you need to do to get the moles into that calculation. But really comes down to reading the question, looking at what the units are, and don't assume that it's something just because it normally is something, because it's not always going to be that, okay? Okay, I kind of skipped this slide, but I feel as though I kind of talked about everything that was already in it. Same deal with that one, so we will move to the next one. So here's a sample question, okay? The other thing you're going to find when it comes to bomb calorimeters, as well as flame calorimeters, is they like to burn weird things on that diploma. And again, I know this year you're not writing the diploma, but if you're watching this video at some later time, you may be writing the diploma. So things they like to burn like food items. For a couple of years, they were really hung up on burning Brazil nuts. There's a good few years before that, it was like Cheetos. Sometimes it's like hot dogs. So the biggest thing to recognize is when they change it to a food item, they are not going to ask you for molar enthalpy. And that's because you don't have a molar mass for peanut butter, right? You can't look that up on your periodic table. It doesn't exist. Same thing with like a hot dog. There is no molar mass. It's a mixture of a whole bunch of different things. So generally, they're either just going to ask you for how much thermal energy, or they're going to ask you for thermal energy per gram. So instead of per mole, you'll just be getting per gram. Okay, so here we have an example. So it says a 16-gram sample of peanut butter was placed in the steel bomb calorimeter. The bomb calorimeter had a specific heat capacity of 8.28 kilojoules per degree C. If the temperature increased by 50.5 degrees C, A, what amount of thermal energy was released by the peanut butter, and B, what is the enthalpy of combustion of the peanut butter per gram of sample? So if we're looking at A, we're trying to solve for the delta CH, right? We're looking for how much thermal energy was released by that peanut butter. So this is just going to be negative, right? Because we always need that negative. So normally I would do MC delta T, but in this case, have a look at the specific heat capacity up here, right? That specific heat capacity is kilojoules per degree C. One of these days, I'm going to get over this cough that I've had for like 2 months. So because this has units of kilojoules per degree C, I don't need the mass, okay? And sometimes you guys want to use this mass of peanut butter. Don't use the mass of peanut butter. We burned that. We are not looking at the mass of peanut butter. So we're going to have negative. Okay, think about the units we're trying to solve for. The amount of thermal energy is just kilojoules. So we're going to use that 8.28 kilojoules, and that was per degrees C, right? And then to get just kilojoules, the only unit I have to get rid of is degrees C. So I'm just going to times by 50, apparently I'm in superscript mode, times by 50, 0.5 degrees C. Right, and now when I look at that, degrees C goes away, and I'm left with just kilojoules. So, really simple calculation. The problem becomes knowing that that is what you have to do, right? And the only way to really know it is to look at what you have been given. Okay, so this is going to equal negative, we got 3 sig digs, so 418 kilojoules. Okay, so there's A. There is more on my calculator though, right? There's 0.14. So because this was a question on its own, I rounded for significant digits. But when I go to do part B, I'm going to make sure that I use that whole number, okay? So what's the enthalpy of combustion of the peanut butter per gram of sample? So we're going to have that delta CH. But now we're looking per gram. So we're going to have that negative 418.14 kilojoules, right? I put those numbers back in that were on my calculator. And I want to get this per gram. So we're just going to times it by 1 over the 16 grams that we had in our peanut butter sample. Okay, now when I look at that, my units are going to give me kilojoules per gram. So I'm just going to divide by 16. And I got that this is equal to negative 26.1 kilojoules per gram. I'll just get that out of superscript. There we go. Okay, so a little bit simpler when you get into bomb calorimeters. Flame calorimeters are probably some of the more complex ones. I didn't really do an example. I just realized that, and I think that's because normally we would be doing a lab on it, which would have a whole bunch of questions. I will either do an example or I'll see, I know there's some diploma questions near the end. If there is one that covers that concept, then we'll look at that one. Let me look really quickly. Not that one, not that one, that one. That one's close, but not quite. Okay, not that one either. Okay, give me a second. I'm going to throw in an additional slide. So this isn't going to be in your note package, but I will make sure that when I post the completed notes that that additional slide is in there. Okay, so here's basically the data table that we would have generated had we actually gone to the lab and done our molar enthalpy of combustion. So normally what we do is we would burn some methanol, we would burn some ethanol, and we would burn some propanol. And then we would determine the mass of all the different items that we have, as well as all the different initial and final temperatures. So really quickly, I'm just going to reopen that lab, only just to kind of show you what the setup would have looked like, okay? Well, I don't have a picture of it. I thought I had a picture of it in here. Okay, but yeah, so basically it's going to look the same as this one here did. The difference is going to be instead of having a candle here, you're going to have a little alcohol burner, okay? So when you look at all the different measurements that we have on our data table, okay, we have mass of the alcohol. So this is how much alcohol we burned that was inside of that little dish at the bottom, okay? Mass of aluminum can. So mass of aluminum can is this calorimeter can that is hanging. Okay, then it said mass of water and the can, and that's just the mass that's in the side of here, right? And we have that so that we can determine the mass of water. What else did we have? We had an initial temperature. And then we had a final temperature. Okay, so the initial temperature, we stick our thermometer inside the water, we get that initial temperature. We then light our sample, and when it's all done burning, we record what the final temperature is. Okay, so let's have a look at the methanol, and we can look at doing this calculation for the methanol. So mass of alcohol was 4.99 grams. So that's how much alcohol we burned. So this is going to get used to get the per mole part. Okay, then we have the mass of the aluminum can. We need that because we need to do the MC delta T of aluminum. we have mass of water and can, and that's because we need to be able to figure out the mass of the water. So to get the mass of the water, we're going to do 239.96, and we're going to subtract 12.86, right? So we're going to do the water in the can minus the can so that we can figure out what the water is, which in this case, I don't know if it's going to let me write over that, so maybe I'll just go into pen mode. It's going to be 227.10. And obviously that will be in terms of grams, okay? So then we have the initial temperature of the water in the can and the final temperature of the water in the can. So if you think about the calculation that we talked about before, we said, oh, nope, that's not what I want to do. I wanted to put the delta symbol in. So we said we would have that delta CH equals, oh, hold on, this is a really weird font for some reason. 24. And I just want a somewhat normal font. Okay. So we're going to have that delta CH equals, okay, we had said, remember, negative MC delta T of the water plus the MC delta T. In this case, our calorimeter is aluminum, okay? Then we have to get this per mole, right? So we would have to do whatever we need to do to get this to give us that. So when we start looking at our calculation, we're going to have negative, and then in brackets, so MC delta T of the water. So for the water, our mass is 227.10 grams. Specific heat capacity of water is 4.19. But actually what I'm going to do is I'm going to change this to kilograms. Okay, the reason I'm going to do that is, remember we talked previously about delta CH and we said it's usually in terms of kilojoules per mole. If I leave this as grams, I'm going to wind up with joules, which isn't what I want. So let's change that really quickly. So 0.22710 kilograms times 4.19 kilojoules per kilogram degrees C. Okay, we need our delta T, so we're going to get our delta T by doing the final minus the initial. So 50 minus 22.5, which gives us 27.5 degrees C. Okay, so there's the MC delta T of the water. Now we have to add the MC delta T of the aluminum. So we had 12.86, oh, I'm forgetting again, 0.01286 kilograms. Okay, and if you do forget, you can always just change it at the end and recognize, but obviously you would have to recognize that you have solved for joules and not kilojoules, okay? Specific heat of aluminum is 0.897. That would be kilojoules per kilogram degrees C. Okay, I'm just going to make this font a wee bit smaller so that we can actually maybe get it all on the same line. Okay, so there's me getting the kilojoules part. We had to do MC delta T of water plus MC delta T of aluminum. Last part we need to do is get this per mole. So we were given a mass of methanol, but we are going to need a molar mass for methanol. So methanol is CH3OH. So we get 32.05 grams, and that's going to be per mole, right? We want to make sure that the moles on the bottom so that we're actually solving by the end for kilojoules per mole. Okay, last thing we need to do is get rid of the grams. So to get rid of the grams, we look at the mass we used. It was 4.99. So we are going to do, well, I don't know if I can squeeze this in here, but I'm sure going to try, times 1. Nope. Just squish everything. No. Okay, times 1 over, and I'm just going to squish this in here. It was what, 4.99 grams. Oh, there we go. We'll just pretend that works, okay? So Now when I look at my units, I can cancel out my grams. In here, everything cancel, right? This kilograms, cancel this kilograms. Oh, I forgot to write my temperature in here. Now it's not going to fit. I knew I was missing something. Hold on. There's another way I can try to make this work. I just have to delete. Whoa, what did I just do? Okay, well, let's just pretend these little tick marks aren't there. And then we should be able to clean this up a little more and get in what we need, okay? Because I forgot to put in my temperature here, 27.5 degrees C. And then, sorry, I'm making a disaster of this question. Okay, but I made it all fit onto the line. All right, so here we go. Now I will talk about this a little bit, just to kind of review what I did, right? So here's the MC delta T of water. We have the mass. We convert it to kilograms so that we would actually calculate kilojoules. Specific heat of water. There's the delta T of water. Then we have to add the MC delta T of the calorimeter. So here we have the mass. Again, we convert it to kilograms. Here's our specific heat. Here is our delta T. I'm just missing an extra set of brackets there. So this gave us kilojoules. Got to make sure that you use these brackets at the beginning and the end. Otherwise, what tends to happen is you guys only apply the negative to the first MC delta T, and you forget to apply the negative to the second MC delta T. So again, I know some of you like to just do the 2 MC delta T's, get an answer, and then throw the negative in. You can definitely do that as well. It's kind of up to you. So we are going to type all of this into our calculator. Making sure we either use brackets or apply that negative at the end. And we are going to get that this is equal to, okay, from this we're going to get negative. My calculator says 170, but looking at our significant digits, I'm pretty sure, how many can we have here? Technically, because this temperature was recorded without a decimal place, technically this 5 is not significant. So there's really only 2 significant digits in that temperature. So I'm going to have to write this as 1.7 times 10 to the 2 kilojoules per mole. Okay. And you'll see when we get into actually calculating theoretically what this is pretty far off from what it should be. But again, we talked about how flame calorimeters are generally going to have huge percent errors. All right, so now we're going to start talking about Hess's law. So Hess's law basically states that the enthalpy change of a physical or chemical process only depends on the initial and final states, not on how we got there. Okay, I normally compare this to like climbing a hill, right? Well, I wouldn't say climbing a hill. Let's pretend you're on a phys ed hike, right? You guys are, I don't know, climbing a barrier lake or barrier mountain, whatever it's called. You have a couple of options of how you're going to get there, right? First option, which I know some of you are like, oh, that's so me, I'm going to do that, is I'm just going straight up. I just want to get there as fast as I can. Second option is I'm not going straight up. That's crazy. I'm taking the switchbacks, right? And you do more of this to get up. Ultimately, though, you both started at the same point and you both ended at the same point. Okay, Hess's law is basically getting at the same idea, that the delta H, or the difference between how much energy my reactants have and how much energy my products have, only depends on what they are, not on whether we went directly from reactants to products or on whether we might have gone it through a couple of different series of reactions to be able to reach it, okay? So this leads us into what we call the additivity method. And there are some other names for it, but I generally call it the additivity method. And I call it that because you're going to be adding up a series of reactions to obtain a desired equation, okay? So you will always know that it's an additivity method question because it's going to give you like 3 4, sometimes 2, but it's going to give you a couple of reactions. And usually it's going to either give you the desired equation or it's going to tell you what it is so that you can create that desired equation. We then are going to manipulate our equations. So when you are manipulating your equations, you do have a couple of choices of what you're going to do. So first option is always to leave the equation or to flip it around. Okay, you're going to make that decision based off of where a particular chemical is in the desired equation. If it's on the reactant side of the desired equation, and it's also on the reactant side in the equation you're manipulating, then you wouldn't flip it because it's on the right side. But if it was on the product side and you needed it on the reactant side, then you would have to flip that equation around. The next option you have is to either multiply, divide, or leave it. Okay, and you're going to make that decision based off the coefficient that you need to have. So again, you're going to look at your desired equation. You're going to look at what is it balanced with in that equation. If it's balanced with that number already in the equation you're manipulating, then you don't need to do anything to it. But if it's balanced with, let's say, a 2 and you needed a 1, then you're going to have that equation so that you can get the coefficient you want. Okay, it might seem a little confusing, but we're going to work through a couple examples and you should see that it's really not that bad. So biggest challenge tends to be with these ones is finding a starting point. Some of you always want to go in numerical order and you're like, well, this equation was given first, so I have to use this one first. And sometimes that's the right approach, but sometimes that isn't the right approach. What you really want to do is find the equation that has something in it that's in your desired equation that isn't in any other equation, because then you know the only way to place that particular chemical is with that equation. There's no other choice. Okay, so examples we're going to look at, some of them are definitely going to show you that. So here's our first one. So the overall equation for the formation of sulfur trioxide from sulfur and oxygen is S8 plus 12O2 to give us 8SO3. So this is our desired equation. Okay, we have 2 equations only to manipulate, so it's a nice easy one to start with. Really, in this case, you could choose to start with either of these. And why I say that is we have S8 in our desired equation. S8 is only in equation 1. So I could choose to start by placing that. I could also choose to start with equation 2 because equation 2 is the only one with SO3 and I know SO3 has to get placed on the product side. Okay? So as we are manipulating these equations, whatever we do to the equation itself, we also have to do to delta H. So if I choose to flip this equation, I need to flip the sign. If I decide that I need to multiply by some number, I also have to multiply delta H by that number. Okay, so let's choose to start with equation 1 because it's a nice easy one to start with. So when I look at equation 1 is going to allow for me to place the S8. I know S8 in my desired equation is on the reactant side. It's already on the reactant side, so I don't need to flip it, I'm going to leave it. Coefficient-wise, they also already match up. So because they already match up, I'm not going to do anything to that first equation. So I'm going to leave that first equation the same. So we are going to have that S8. Sorry, I can't see what I'm typing. I put a star in. I did not mean to do that. S8. I'm just going to leave states out because it's a lot of typing on my part. But we can add them back in at the end. Okay. So 8SO2. Giving us 8SO2. And I'm having issues because that's not an SO2, that's just an O2, okay? So here's our first equation. We literally did nothing to it. So because we did nothing to it, that delta H is going to stay exactly the same. Okay, nothing about it is going to change. No clue why my computer is being so weird today. It's definitely having issues. Come on. Hold on, let me pause this. Okay, so delta H is going to stay the same because we didn't actually do anything to manipulate this equation. So now let's look at equation 2. So first decision we need to make is to leave it or flip it. We are going to choose to leave it because the SO3 is on the product side, which matches the SO3 over here. Next decision is, do we need to multiply, divide, or leave it? Well, if I look at my desired equation, it has a coefficient of 8. Right now I only have a coefficient of 2. So we are going to have to multiply this entire equation by 4 so that we can get those coefficients that we want. So we're going to wind up with 8 SO2 plus 4 O2 to give us 8 SO3. Okay, and now, because we multiplied by 4, we are going to have to do the same thing to our delta H. So we are going to have to go, close that, and we're going to have to do, in our calculator, negative 198.4 times 4. And we're going to come up with negative 793.6 kilojoules. Okay, now what we need to do is we need to add them together, hence why it's called, that's why it's called the additivity method. So, similar to when we were in redox and we were combining equations, if something is on both sides of the arrow, right, so this 8SO2 is going to cancel that 8SO2 because they're on opposite sides. Okay, there's nothing to do with the S8. These oxygens are going to combine, and this is going to stay as it is. We're then going to take these two delta H's, and we are going to combine them together or add them up. Okay, so we wind up with S8, that was a solid, plus 12O2, right, because we had 4 plus 8, to give us 8SO3. Okay, then we got to figure out what delta H is going to be. Okay, so delta H, to get that, we are going to add those two numbers up. Make sure you remember when you are adding that you are using addition sig-dig rules. So because these both had one number after the decimal place, my answer should also have one number after the decimal place. So I'm going to come up with negative 3,168 kilojoules for this particular equation. Okay, now we're going to look at one that is a little more complicated, right? The last one literally only had 2 to combine. You're generally going to find we ask you to combine between 3 and 4, okay? So from the following equations, determine the molar enthalpy of formation. So molar enthalpy of formation always means forming that compound. So if we're forming HNO2, we would be needing hydrogen, nitrogen, and oxygen. You'll notice we have balanced with fractions. The reason we do that in thermo is if we're trying to find the molar enthalpy of formation, we need to form just a single mole, which means at that point I'm going to have to use some fractions in here to be able to account for that as we move forward, okay? So that is my desired equation. I need to use these 4 to get that one. So this is where sometimes you guys are like, I want to start with equation 1 because it's the first one that comes into play. The problem though is I don't really know how to place it, right? NH4NO2 isn't in my desired equation. Neither is water. And some of you guys will be like, oh, that's okay, Miss Chip. Here's the nitrogen. We know it has to go over here with a half. But here's the problem. This equation also has nitrogen. So if I place this with a half, what am I doing with this, right? So you're always going to find that you need to use all of the equations. This is one of those cases where they are never going to give you extra equations. If you get to the end of the question and you haven't used something, I promise you, you have done something wrong. And it doesn't seem to matter how many times I say this. I've definitely given some quizzes where you guys come back and you're like, oh, Miss Chip, like I didn't use all the equations. You tried to trick me. And it was like, no, definitely didn't try to trick you. You should have used all the equations. So I'm not going to start with number 1 because number 1 doesn't have something in it that is exclusive to my equation. So let's look at equation 2. It has ammonia. I don't know where that goes. That's not in my equation. Okay, it has HNO2. That's promising, right? HNO2 over here. It's in here. Let's see if HNO2 is in any other equation. It's not in equation 1, it's not in equation 3, and it's not in equation 4. So starting with equation 2 would work because I know that HNO2 has to go over here, and I know it has to go with that coefficient. So I'm going to take equation 2 and I'm going to flip it. And I'm going to flip it because I know the HNO2 needs to be on the other side. So we're going to have NH4 NO2 AQ turning into NH3 gas plus HNO2 AQ. So thinking about what we just did to that equation, let's see if this is going to let me copy a delta. So thinking about what we just did in that equation, all we did was flip it. So we are going to flip, my goodness, my computer doesn't like me today. Okay, apparently it's just gone into a super small font. We'll go with that. So because we flipped the equation around, we are going to flip the sign. It's going to be positive 37.7 kilojoules. Fix that font up. There we go. Okay, so we have now used equation 2. We can't use it again. Once you use something, that's it. You are done using that particular thing. So now we need to decide what equation we want to use next. So if we look at this, we've placed our HNO2, but we have ammonia. We know we don't want ammonia. That's not in our desired equation. We also have NH4NO2, which we also know that we don't want because it's not in our desired equation. So we could choose to cancel either one of those. Because the NH4NO2 comes first, I'm going to choose to cancel that one first. So the only other equation that has NH4NO2 is number 1, right? It's right here. For me to be able to cancel this, though, I need to flip this equation around so that the NH4NO2 is over on the product side. So I don't need to change the coefficients because it already matches up with what I have. So we are going to have N2 gas plus 2H2O as a liquid turning into NH4 NO2 AQ. Okay, here for our delta H, we are going to have the delta H is equal to, so what did we do to this equation? All we did was flip it around. So positive 320.1 kilojoules, because all we did was flip it around. I forgot to write an H there, so let's fix that. Okay, so now we have used equation 1 and equation 2. Now we have to use equation 3 and 4. So looking at what we have so far, right, we have canceled this with this, right? That was why we used that. So we need to get rid of the ammonia. So equation 3 has ammonia, but it has a coefficient of 2. So I'm going to have that equation, right? Because 2 divided by 2 equals 1. So sidewise, I get to leave it because it's on the reactant side and currently it's on the product side, so they are opposite. So we're going to have NH3 AQ turning into, so 1 divided by 2, so 1/2 N2 gas plus 3/2 H2 gas. Okay, our delta H is going to equal, so what did we do to this equation? All we did was halve it. So we're going to take 169.9 and we're going to halve that. So we're going to divide by 2. We get positive 84.95 kilojoules. So now we have used equation 3, and that has allowed for us to do this, right? If we look, we also can reduce some more, right? We had an N2 over here and half of an N2 over here. So we can get rid of this and turn this into a half. Okay, so we're definitely getting closer because look at this desired equation. We need a half of an N2. We have half of an N2. We needed the HNO2. We have that. We still have water and hydrogen over here, which we know we don't want, but that's okay because we have not used equation 4 yet. So looking at equation 4, I need to be able to get rid of the water. Okay, so right now it's on the reactant side. Here it's on the product side, so that's good. But they don't have the right coefficients, right? This has a 2, this has a 1. So I'm going to have to double equation 4 so that I get the coefficients that I want. So I'm going to have 2H2 gas plus, so if I do half of an oxygen times 2, I just get an oxygen. So plus an O2 gas to give us 2H2O liquid. Okay, one thing you really want to watch for when you do these questions, sometimes you guys get lazy with states, and I know I sometimes do too, like in the last question. Really make sure you write the state of water, because you're going to find that you will get questions that water is in here in different states, sometimes as a liquid and sometimes as a gas. And if you don't write that state, you may cancel a liquid water with a gas water. And usually that's when you guys find that you didn't have to use all of the equations. So do make sure you are watching for that. Okay, the delta H, what did we do to this equation? We doubled it. So we're going to do negative 285.8, and we are going to double that. So we're going to get negative 571.6 kilojoules. Okay, so let's see what else we can cancel now. Okay, this water is going to cancel this water. Okay, we have some hydrogen here, and we have hydrogen here. We have 2 H2s, we have 3 halves H2. So 2 minus 3 halves is going to give us 1 half. So if we look at this, we're left with a half of an N2 plus a half of an H2 plus an O2 to give us HNO2. And that was our desired equation. So now we just got to add it all up and figure out what we're left with. So we're going to have our 1 half N2 gas plus our 1 half H2 gas plus our O2 gas to give us that HNO2 AQ. Okay, looking at our delta H, so we have to get the sum of all of those. So 37.7 plus 320.1 plus 84.95 minus 571.6. So I come up with negative 128.9. Okay, in 1 decimal place, because when we look back at all these starting numbers, they all had 1 decimal place, and that's going to be kilojoules. Okay, so all in all, this is probably a pretty simple thing. I can tell you the biggest issue you guys have is when you get into these questions here. So this is the last one in your notebook package under this topic. When you guys hit questions like this that are multiple choice or numeric response, you don't want to write anything out because you're like, no one's marking my work. Why would I write it out? I'm going to do it in my calculator in my head. The number of times you guys come back and look at your work on questions like this and say, I just made a really stupid mistake. And it always comes down to, I didn't write anything and I messed this question up. So simple concept, but also really easy to make a stupid mistake if you are not paying attention. So even if you're like half scribbling and it's barely legible, write stuff out for these questions, because otherwise you tend to forget where things are. Or look at this question. There's H2O2, there's H2O gas, there's H2O liquid. There's so many things that have really similar formulas that you tend to misrearrange them. Okay, answer for this one is B, so if you want to give that one a try, I would strongly recommend it. If you were writing the diploma, I'd be like, you should do this question because the Bombardier Beetle shows up on just about every single diploma. But yeah, there's a couple of diploma questions for you to practice. They talk a little bit about flame calorimeter, right? So there's a sample of one. There's some of that additivity concept. Here's another additivity question. They've just given you the information in a graph instead of by just writing out what the delta H is, right? So there's that additional step of being able to interpret it. Here's some manipulated, responding, and controlled variable question. Those are always on the diploma to make sure that your skills are up to par. And then here's another one of those additivity method questions for you guys to give a try, okay?